All right, so today what the plan is to review what we did on Wednesday. So that involves talking about the mean value theorem some more, L'Hopital's rule a little bit more, and parametric curves a little bit more. But ultimately, I want to make sure we have a decent chunk of time to talk about integrals, chapter 5. Let's get going. First of all, let's just review the mean value theorem that we talked about on Wednesday. This is the statement here in red. It's a theorem, it's abstract, it's got hypotheses, assumptions you need to make. Suppose f is a real valued function, that just means real number outputs, which is continuous on a closed interval from a to b, that includes the endpoints, and differentiable on the corresponding open interval from a to b, that does not include the endpoints. And today I will talk about why it's good to have these slightly different intervals here. There's an example that satisfies exactly what we see here, yet the conclusion of the mean value theorem still holds. Then there exists a number c between a and b, so that f prime of c equals f of b minus f of a, all divided by b minus a. I emphasized on Wednesday that this makes good intuitive sense if you think about it graphically. Draw a typical kind of graph here in purple. That's my graph of my function f. My interval here is from a to b. This is saying there's some number c between a and b where the slope of the tangent line, that's the derivative, at that point is the same as the slope of the secant line between these 2 points on this graph. So you can see there's the point a comma f of a, there's the point b comma f of b. That secant line connecting those dots has slope equal to this because it's rise over run. At c, which is right about there, right here on the number line, f prime of c is equal to f of b minus f of a. These two lines are supposed to be parallel. This tangent line is parallel to that secant line. So it seems perfectly reasonable. We also looked at an example last time, x squared. Let's look at a couple more examples today. Let's try x cubed. So f of x equals x cubed. And I can pretty much take anything that I want for a and b. Let's pick a to be 2 and b to be 5, just to pick something. This is certainly a nice function. It's nice and continuous everywhere. It's nice and differentiable everywhere. So the mean value theorem should apply to this function on the interval between 2 and 5. There should be some number c between 2 and 5 where the derivative of this at c equals the slope of a secant line between the corresponding points. In fact, we could draw a quick little sketch here. If a is 2, f of a is 2 cubed, that's 8. And if b is 5, f of b is 5 cubed, that's 125. So the rise here of the secant line that I'm going to draw here is 125 minus 8, which would be 117. All divided by the run, that's 3. F of b minus f of a divided by b minus a is going to be 125, 5 cubed, minus 8, 2 cubed, divided by 5 minus 2. Again, that's 117 over 3, and that is 39. So the mean value theorem says there's some number c between 2 and 5. It's between 2 and 5, where f prime of c equals 39. Well, what is f prime of c? F prime of x would be 3x squared, so f prime of c would be 3c squared. If I set this equal to 39, I can solve for c. C is going to be the, well, plus or minus square root of 13, but the c that's between 2 and 5, in fact, is plus square root of 13. C is square root of 13. That's the one between 2 and 5. Square root of 13 is going to be somewhere between 3 and 4, in fact. 13 to the 1/2 power. Yeah, it's about, C is approximately 3.60555. okay? It's a little closer to 5 than it is to 2. Just a little bit closer to 5 than it is to 2. It's not halfway between them. Right about there, the slope of the tangent line is the same as the slope of the secant. I'll show you another example. And this other example illustrates why we make the assumptions in the way we do. This example is going to be continuous on a closed interval, but actually just differentiable on the corresponding open interval, not at the endpoints. And that example is f of x equals the inverse sine function. You can also write that as the arcsine. Its domain is the interval from -1 to 1. Its graph on that interval looks about like this over here and this over here. Inverse sine of 1 is actually pi over 2. Inverse trig functions can be thought of as giving you outputs that are angles, though we're not drawing it like an angle. But pi over 2, you know, would correspond to 90 degrees. And inverse sine of -1 gives you negative pi over 2. And it turns out this function is certainly continuous. This is continuous on the closed interval from -1 to 1. But it's not differentiable at the endpoints. It's differentiable on the open interval and not at the endpoints, because at the endpoints, I didn't draw it perfectly, but there's actually vertical tangent lines. It's not drawn perfectly. The tangent lines, as you approach the endpoints, approach vertical and approach infinite slope, which makes sense when you think about its derivative, because its derivative, which you memorized for the gateway, is 1 over square root of 1 minus x squared, which is technically undefined when x is plus or minus 1, though that's not it's actually not a proof that it fails to be differentiable at plus or minus 1, just an indication that it probably is not. But it does satisfy the hypotheses of the mean value theorem. There's got to be at least one number c between a and b, between -1 and 1, where the slope of the tangent equals the slope of the secant. I'm taking a to be -1, b to be +1. F of b minus f of a divided by b minus a. It's going to be inverse sine of 1, which is pi over 2, minus inverse sine of -1, which is negative pi over 2. B minus a is 1 minus -1. This simplifies to pi over 2. That's the slope of that secant line there. It's about 1.57 for the slope. What values of c will the derivative equal that there? Well, I'd have to just plug in c for x. I don't have to call it c, but I might as well. And solve for c. Looks hard. Not quite as hard as it looks. You can get rid of the square root by squaring both sides. So you get pi squared over 4 equals 1 over 1 minus c squared. Then you could cross multiply effectively. Well, multiply both sides by 1 minus c squared, and also multiply both sides by 4 over pi squared. That's what I did there. I multiplied both sides by 1 minus c squared to cancel it on the right side and give me a 1 minus c squared on the left side. And then I also multiplied both sides by 4 over pi squared to cancel that on the left side and get it on the right side. If you solve this for c squared, you get c squared is 1 minus 4 over pi squared, which is pi squared minus 4 over pi squared. And that means c is plus or minus the square root of that thing, which will be plus or minus the square root of pi squared minus 4 over pi. And I believe these numbers, I checked it out beforehand, are close to 0.7 something. I guess I can do it quick here. Pi squared minus 4 square root divided by pi. Yeah, these are approximately plus or minus 0.77. So right about here and here, you've got tangent lines that are parallel to the secant line. Again, my drawing is not perfect, so it might be a little misleading if you don't draw a perfect drawing. Okay, so the theorem still applies to this situation, even though the function's not differentiable at the endpoints. What is the theorem good for? This is kind of funny, but to a mathematician, a theorem is important. A theorem is good, useful, if you can use it to prove other theorems, like the increasing function theorem. Now, that can be justified more from, say, an engineering or scientist standpoint by saying ultimately things like the increasing function theorem are useful because you can use them to, for example, justify the first derivative test. And that is a useful test for finding local extreme points. In fact, it's especially useful when you generalize it to higher dimensions in multivariable calculus, where graphs are not so easy to make if they're even possible to make at all. So that's something real advanced that generalizes all of this, and you definitely need some advanced theorems to know what to do in higher dimensional situations. What does the increasing function theorem say here in this one-dimensional situation? Same kind of setup as the mean value theorem. Suppose f is real valued, meaning real number outputs, continuous on a closed interval from a to b, and differentiable in the corresponding open interval. If f prime is always positive over the entire open interval, then f is strictly increasing, in fact, on the closed interval. Okay, so if the derivative is always positive, tangent lines are always have a positive slope, the function's got to be going up. There's no way it could even have one little piece of it that goes down at all. So that's something you should know. There's also a decreasing function theorem that says if f prime is negative for all x in the interval, then f is decreasing on the interval. But I also said, as a word of warning, just to realize that something called the converse of this is not true. If a function is strictly increasing on an interval, it does not mean the derivative is always positive. And the simplest example, again, of that is f of x equals x cubed. That's a function that's always increasing, but it's flat enough, so to speak, near the origin that its derivative at 0 is 0. The graph does look more and more horizontal the closer and closer you zoom in on the origin, though it's never exactly horizontal. It just looks more and more horizontal. Okay, so some subtle things there to realize and are worth knowing and could be quizzed about, like, well, could have true, false, or multiple choice questions related to this kind of stuff on the next exam. So it's definitely worth thinking about. Do you have any questions about that? Okay, let's do some more examples with L'Hopital's rule next. Let's pick a few problems from the book. Oh, let's say take a look at number 2 first, for example. Take the limit as x goes to 1 of this rational function x squared plus 3x minus 4 over x minus 1. First thing you should always do when you're approaching a problem like this is you should check, do I even need L'Hopital's rule? If you don't need it, if it doesn't apply, don't use it. You'll get the wrong answer. Is it a 0 over 0 indeterminate form or an infinity over infinity? That's the kind of thing you need to think about. In this case, how do you decide? Plug in the number 1 into both the top and the bottom. In either case, you get 0. 1 squared plus 3 times 1 is 1 plus 3 is 4, minus 4 is 0. 1 minus 1 is 0. This is a 0 over 0 indeterminate form. So therefore, I can use L'Hopital's rule. This is, again, a 0 over 0 indeterminate form. You should always check that, again, because if you don't, and you apply L'Hopital's rule anyway, you'll get the wrong answer. We can use L'Hopital's rule. We can form a new limit with a new fraction whose numerator is the derivative of the original numerator, in this case 2x plus 3, and whose denominator is the derivative of the original denominator, in this case 1. Right? The derivative of x squared plus 3x minus 4 is 2x plus 3, and the derivative of x minus 1 is 1. That's an application of L'Hopital's rule. It is not the quotient rule, okay? Don't ever think L'Hopital's rule is the quotient rule. Nothing to do with it, okay? Differentiating the top and the bottom individually and making a new fraction. But now that's a limit that can be computed just by substitution because it's a nice continuous function. At x equals 1, just plug in 1, get 2 times 1 plus 3 is 5. There's the answer. You could try confirming it, either by plugging numbers in or by graphing. We graph this function, x squared plus 3x, x squared plus 3x minus 4 divided by x minus 1. Technically speaking, this graph near 1 is going to have a hole in it. It's one of those graphs with holes. In fact, it looks straight. You might wonder why. We'll see if we can figure it out. What happens as x gets close to 1? Y gets close to whatever the y coordinate of that point is. Let's zoom in a bit closer. We trace this. When x is close to 1, y is close to 5. It says when x equals 1, exactly y is technically undefined. There's technically a hole in the graph, which actually, it looks like on my calculator, there's actually a tiny little space there, like the calculator knew to make a little space there. A missing point. Maybe it did. Maybe it was programmed. I didn't realize it did that. Is there a way to figure this out some other way? In fact, this is something that we did a bit back in chapter 1. You can factor this rational function and cancel the common factor. X squared plus 3x minus 4 does have a factor of x minus 1. It's x minus 1 times x plus 4. And those can cancel and leave you with a limit as x goes to 1 of x plus 4, which is 1 plus 4, which is 5. So you can find the answer in this case in another way. Remember that technically this is valid to go from here to here because technically speaking, it doesn't matter what happens at x equals 1. These two expressions here and here are equal as long as x is not equal to 1. So their limits are equal. This one, it's easy to see the limit is 5 because it's a nice continuous function. In fact, it's that straight line we were just looking at on the graph. It's a straight line with a slope of 1 and a vertical intercept of 4. This graph is the same line except with a hole in it, a point missing at the point 1, 5. But the limit still exists. The limit still equals 5. Stop me if you want me to clarify anything. It also helps me know that you're there. Feeling lonely on this end. Let's try number 4. Limit as x goes to 0 of e to the x minus 1 over sine x. First thing again, is it a 0 over 0 indeterminate form? Always check that first. Do the top and the bottom both go to 0 as x goes to 0? E to the 0 minus 1 is 1 minus 1 is 0, and sine of 0 is 0. Yes, this is a 0 over 0 indeterminate form. I can therefore use L'Hopital's rule. I can take the derivative of the top and the bottom individually and compute this new limit. This is not a 0 over 0 indeterminate form anymore. Because if I plug in 0, I don't get 0 over 0. I get, in fact, 1 over 1. The answer is 1. Right? E to the 0 is 1, and cosine of 0 is 1. You got to know your facts. You got to know that cosine of 0 is 1, sine of 0 is 0. Okay? So there's a way to do this with L'Hopital's rule. Is there another way to do this? Doesn't seem to be, because we can't do any factoring like we did here. Seems like there's not another way to do this. There actually is. It's related to something called Taylor's series, which you'll learn about in Calculus 2 if you take that. Taylor's series can help you have a new way of evaluating this limit. You're also going to have some questions due on Monday related to dominance. Which function dominates as x goes to infinity? We actually talked about this in chapter 1, and we treated it as just a thing to memorize. But let's go ahead and take one of these examples. Let's take, say, this example here. Which function dominates as x goes to infinity? Natural log of x plus 3 or x to the 0.2? By dominates, we mean which function grows faster ultimately. And what we said back in chapter 1 was that powers of x, power functions with positive powers, even if that positive power is small, like 0.2 or maybe even smaller, like 0.00001 or something, will always dominate any logarithm. They will always ultimately go to infinity faster. How do you verify that? And do we want to verify it? It doesn't say to verify it, but let's see if we can do that. What we want to do to verify that is we want to verify this equality right there. The function g is said to dominate the function f as x goes to infinity if the limit of f divided by g is 0. And we might be able to use L'Hopital's rule to see if that happens here. So again, we think x to the 0.2 dominates the natural log of x plus 3. Let's see if L'Hopital's rule confirms that or not. Sometimes L'Hopital's rules, I mean, it's always true, but sometimes it's not helpful. Sometimes you have to apply it more than once. We talked about that on Wednesday. And sometimes it just doesn't really help much. We claim that x to the 0.2 dominates natural log of x plus 3 as x goes to infinity. What I'm hoping will be true is I'm hoping this limit of the natural log of x plus 3 over x to the 0.2, hoping this limit is 0. If this limit is 0, that means the bottom of the fraction is growing big faster than the top is, significantly faster, enough to make this fraction go to 0. Well, is it something we can apply L'Hopital's rule to? It's not a 0 over 0. It's an infinity over infinity. Both the top and the bottom are going to infinity as x goes to infinity. It's an infinity over infinity indeterminate form. That is another situation where we can try to apply L'Hopital's rule and hope that it actually helps. So once again, you differentiate the top and divide by the derivative of the bottom. And you would get that. May not seem like it was ever very helpful though. Look at this and it looks like, well, did this really help? It's not so clear. I think it would be good to rewrite this in another way to simplify this fraction. And this is always a good idea as well. Before you go trying to use L'Hopital's rule again or something, try to simplify whatever expression you got. One way we can simplify it is to realize that dividing by 0.2 is the same as multiplying by 5, because 0.2 is 1/5. So that's one thing we can do is we can write a 5 Also, having x to the negative 0.8 in the bottom of the fraction is the same as having x to the positive 0.8 in the top of the fraction. I can put an x to the positive 0.8 up top, and that x plus 3 there still stays down here. Okay, so I've simplified the expression a bit. Technically, as this is, it's still an infinity over infinity indeterminate form. Though it is in a form that makes it, well, maybe even without using L'Hopital's rule, makes it a little bit more clear that this thing goes to 0, because I got a first power for the highest power of x down here and a 0.8 power up here. A first power is going to grow faster than a 0.8 power. Well, this should go to 0, but maybe we better try L'Hopital's rule again just to make sure. Differentiate the top, bring down the 0.8, get a 4. X to the 0.8 minus 1 is negative 0.2. Derivative of the bottom is just going to be 1. Okay, that was good that we did that. This is now no longer an infinity over infinity. This is 4 times x to the negative 0.2, which is the same as 4 divided by x to the positive 0.2. And that's definitely something that goes to 0 as x goes to infinity. A constant divided by something that's getting bigger and bigger, arbitrarily big, in fact, is going to make this fraction go to 0. Therefore, all these calculations, including 2 applications of L'Hopital's rule here and here, verify this limit is 0. That means this is true. X to the 0.2 dominates natural log of x plus 3 as x goes to infinity. I know from experience in teaching this that people seem to have trouble with L'Hopital's rule. Okay. I would encourage you, besides any homework I assign, to look for more practice. It just seems to be a rule that trips people up. And they're not quite sure how to use it when it comes to exam time. So make sure you practice.
I had a quick question.
Yeah.
I don't know, this might be very wrong, but I just got it in my head. When you're using L'Hopital's rule, if it doesn't get to an indeterminate form and you can't use L'Hopital's rule, are you able to then use, was it f of x minus the chain, f of x minus h minus f of x over h squared? Can you use that formula to find the limit if you can't use L'Hopital's? Or is that...
I'm not quite sure what you're referring to. It sounds like maybe you're referring to derivatives and the difference quotient.
Yeah, like the instantaneous, yeah, the difference quotient.
Yeah, I mean, it's possible that it's in a form where that might be valid, but not typically.
Okay, thank you.
Typically what happens is you come up with a situation where you can either just plug the number in because it's continuous, like here, or here, or here, or you end up with something like this where it's pretty obvious the answer is 0 just by looking at it and thinking about it.
Okay,
those are the 2 typical kinds of things that happen.
I was doing too much work, I guess.
Okay, yeah. You always want to avoid, you want to be able to avoid L'Hopital's rule if you can. It's nicest when you just have some limit where it's easy to plug the numbers in and just get an answer because the function's continuous. But the purpose of the rule is to deal with situations that are not so nice. But you do need to check that it's a 0 over 0 or infinity over infinity. The book mentions some other special cases as well, and they show you some manipulations to help you do those problems. I'm not assigning any of those at first. Maybe on Monday we'll talk about 1 or 2 of those kinds of problems as well. All right, let's move back on to parametric equations and curves again. Let's do an example in the book. Let's take a look at number 46, section 4.8. For x and y in meters, the motion of a particle is given by these 2 equations. These are parametric equations in the parameter t. You want to imagine t is time. And then as time goes by, these 2 equations give you different x and y values that that will generate a curve. And it's the curve of motion of a particle in this case. Though you could pretend that, again, that it's you driving in your car in a parking lot or something, or maybe a bug walking on the pavement. Question A, does the particle ever come to a stop? If so, when and where? B, is the particle ever moving straight up or down? If so, when or where? And part C, does it ever move straight horizontally, right or left? All right, let's see what we can do with these questions here. This is section 4.8, number 46. The book doesn't call it f of t and g of t, but I think I will. X equals f of t is t cubed minus 3t. Y equals g of t is t squared minus 2t. Again, the first question is, does the particle ever come to a stop? Well, it's going to come to a stop if the speed is 0. Even if it's 0 just for an instant in time, which can happen. We know from free fall that if you throw a ball up in the air, there is one instant where its speed is 0 when it reaches the top of the motion before coming back down again. So you can talk about an instantaneous speed of 0 where the particle stops just for one moment in time. Let's see if we can figure that out by going ahead and computing the speed. Remember that the speed is the square root of f prime of t squared plus g prime of t squared. And actually, before we compute this, maybe we should get an intuitive idea about whether it's going to be true or not. Let's go ahead and plot it. So remember, go to your mode, go to parametric mode, y equals. So our example here, f is the x coordinate, that's t cubed minus 3t. By the way, the t's show up just when I press the x button when I'm in parametric mode. And y is t squared minus 2t. All right, let's just see what happens. If I plot this for t going, say, from -3 to 3, I'll make it go slower by doing a small t step, say 0.01. X going from like maybe -5 to 5. Same for y. Let's just see what we see. Okay, graph it. Ready? Watch the motion and try to see if there's ever a moment in time where it looks like the speed is 0. Interesting. I think the speed was probably 0 at that corner, right? Where it's coming along this way, and then it kind of turns around. Sharp corner, whatever value of t you're at this point where x looks like it's -2 and y is -1, looks like probably a spot where the speed was 0. Let me try to graph it again. Just change the t step slightly to get another graph. Ready? 1, 2, 3, go. So there's the motion. It goes kind of fast. It's slowing down, then it speeds up a little bit, slows down. Yeah, right now, turned around. One instant in time where the speed is 0. Let's see if we can confirm this with the calculation here. So I've got to find f prime of t. It's 3t squared minus 3. Got to square that. Just differentiated this here. F prime of t is 3t squared minus 3. G prime of t is 2t minus 2. Got to square that. And let's go ahead and simplify this. So I'm going to be foiling in my head. 3t squared minus 3 times another 3t squared minus 3. I'll get the 9t to the 4th Should be a minus 18t squared and then a plus 9. And then if I square this, I get a plus 4t squared minus 8t plus 4. Square root of 9t to the 4th minus 14t squared minus 8t plus 13. I did not make a mistake. Look good? Anybody see a mistake anywhere? I think it's good. That's the speed. It's not clear that that's ever 0 just by looking at it. Let's confirm it does equal 0 somewhere with Mathematica. So let me go ahead and change the f of t and g of t here. T cubed minus 3t f and t squared minus 2t for g. Let's do the parametric plot manipulate thing here. Start, but our time interval will go from -3 to b, where b just starts out barely to the right of -3, like -2.999, goes up to 3. Probably need a bigger plot range. Let's make it 12 here. So we'll see the same kind of motion we saw in the calculator. There it is. What's the speed function though? Expand it. It's not expanding it. Simplify maybe. Okay. Okay, it did write it actually in a more useful form than what I wrote by hand. So what I wrote by hand was this. It's actually more useful to write it like Mathematica did, because what this is showing you is it's writing it as the thing under the square root is this product. That's going to be 0 for one thing if t is 1. That's what that's showing you. -1 plus t, or t minus 1 squared, is a factor under the square root. That's going to be 0 when t is 1. T is 1 is a place where the particle stops. It's an instant in time where the particle stops. In fact, it is the spot. Let's see if it happens at b equals 1. Let me go ahead and enter a 1 here. Yeah, it is at the spot where it turns around. X is -2, y is -1. In fact, we could also confirm that by plugging in 1 into f and g. We should get -2, 1. Yep, or -2, -1, excuse me. X is -2, y is -1 at this point right there. If we plot the speed, we do see it's 0 when t is 1. Okay, that's the speed function. So that's the answer, is speed of 1 is 0. I mean, you can plug in 1 here to double check it. 9 minus 14, when you plug in 1, gives you -5 plus or minus another 8, -13 plus 13 is 0. Speed of 1 is 0, so the particle comes to a stop. Maybe with the word stop in quotes, because it doesn't stop for more than an instant at t equals 1. And x equals f of 1 is 1 minus 3 is -2. Y equals g of 1 is 1 minus 2 is -1. That's the location where it stops. Second question is, does the particle ever move straight up or straight down? is the tangent to the curve ever vertical? I mean, this curve here. Yeah, it looks like it's vertical right there. Is that the only spot where it's vertical? Yeah, it looks like it probably is. What would it mean for the motion to be vertical? It would mean technically speaking, that the rate of change in the x direction is 0. F prime of t would be 0, where g prime is not 0. Does that make sense? I don't know if I can explain that really well. To get into a full explanation of it requires vectors. The idea of a velocity vector, which I don't want to get into. But when it does travel vertical, that instant in time where it's going, where it's traveling along here, and that instant right about there, where it's vertical, that means the rate of change of the position in the x direction is 0. F prime, which is telling you the rate of change of x with respect to t, is 0 at that instant. Where is f prime equal to 0? Well, you'd have to set that equal to 0 and solve for t. F prime of t equals 0 implies 3t squared minus 3 equals 0, implies t squared minus 1 equals 0, t squared is 1. So t is plus or minus 1. But actually only one of these is the spot where it's vertical. To truly be vertical, g prime must not be 0. Now g prime of t equals 0, looking at the formula for g prime, when 2t minus 2 equals 0, which means t minus 1 equals 0, which means t is 1. That's the spot, t equals 1, where we had the corner in the graph. And the motion was not vertical or horizontal. So it's the other value of t equals -1, where f prime is 0, but g prime is not. So the motion is vertical when f prime of t equals 0, but g prime of t is not equal to 0. That happens when t is -1. Because f prime is 0 at plus or minus 1, but g prime is 0 only at plus 1. So at the other one, at -1, f prime will be 0, but g prime will not be 0. And that's when the motion is vertical, as we saw in the picture. We saw it's also never moving horizontally straight right or left. That would happen if g prime were ever 0 where f prime is not, but g prime is only 0 when t is 1 and f prime is already 0 there. So the motion is never horizontal. Okay. Kind of tricky to realize how to think about it. That's just something to take to the bank. These parametric curves are going to describe motion that's vertical, for example, when f prime is 0, but g prime is not, and horizontal where g prime is 0, but f prime is not. Motion's never horizontal since there's no spot where g prime is 0 and f prime is not. G prime is only 0 at t equals 1, but f prime is already 0 there because it's 0 at plus or minus 1. So kind of tricky, but if you draw the graphs and think about the algebra in terms of those graphs and what we saw, then it makes sense. All right, take a breath. This is all to lead us now to chapter 5. Chapter 5 is on definite intervals. So again, we've done indefinite intervals before because that's just doing antiderivatives. Definite integrals are a harder concept. But the key thing to realize right at the start is they are very much related to areas under curves. Okay, so that's the key initial thing to think about, is definite intervals are related to areas under curves. Let's think about this example. Well, maybe we should do a simpler examples first. Okay, let's do some simpler examples first. Section 5.1 introduces definite integrals by the idea of trying to, they phrase it as how do we measure distance? How do we measure distance traveled? Okay, which is what these parametric curves and the speed are related to. The speed, like I mentioned on Wednesday, can help us figure out the distance traveled. Let's build it up in special cases, simple special case. Special case number 1 is if your speed is constant. Call the constant c. Okay. Question is, how far do you travel from time 0 to time some unspecified amount of time, call it t, if you're traveling at a constant speed c? Well, that's one of your favorite formulas, or should be. Distance equals rate times time. You might remember in that first lecture that I shared with you, that was one of the key equations that we're generalizing in all of calculus. We've actually already generalized it a lot with derivatives, because it also says rate equals distance divided by time, which is really the kind of thing that we're doing when we do derivatives. We're finding a change in position, for example, divided by a time elapsed. That's giving us a rate of change, a slope. And it's a constant rate if the speed, for example, is indeed constant. In general, this is an average rate, an average speed. This formula here only applies for a constant rate, constant speed. And this formula here, well, it actually applies all the time, though it gives an average rate in general, rather than an instantaneous rate. It gives an average rate. But this formula is generalized to derivatives. This formula is generalized to integrals. We can apply it now. How far do you travel from time 0 to time t? Call that, how about call it dist of t? We got a speed of t. Speed of t for the speed as a function of time. How about a dist of t for the distance as a function of time? Well, just do rate times time. C times t. Done. That's the distance function. Distance equals rate times time. C is the rate, t is the time. Of course, in real life, you'd want to use units. And the common unit for C to be used would be, say, in meters per second. And the common unit for t would be, say, in seconds. So this would be meters per second times number of seconds elapsed. The seconds would cancel, giving you an answer in meters. But of course, you could use different units if you're thinking about a different situation. This can be realized graphically as well as an area under a curve. If I graph the speed as a function of time, and if it's truly constant, then its graph is going to be a horizontal line. From time 0 to time t, okay, I'm going to abuse notation here. I'm using the letter t in two ways, both as a label for the axis, a variable, and as a number, a specific number. Don't let it bother you. Maybe to avoid the ambiguity here, maybe I'll just label the axis time here instead. T is a specific positive moment in time, but it could be any positive moment in time. C times t is the same as the area of this rectangle. Its base is t minus 0 or t, and its height is c minus 0 or c. Base times height is t times c, or which is the same as c times t. The area is the same as the distance. Dist of t equals area of t is c times t. This observation that the distance traveled is the same as the area under the speed graph generalizes to any kind of speed graph. Any kind of speed graph, no matter how crazy it is. The area under the speed graph will still be the distance traveled. Let's see if we can believe it in the next special case. Special case 2. Say the speed is not constant, but let's say it's a linear function. Oh, what should I pick? How about mt plus b, linear function, where m and b are constants. Okay, I could pick specific numbers for all these things. I could have picked a specific number for C. I could pick specific numbers for M and B. But I want you to be able to handle generalizations too. What's the distance traveled is the question again. Let's pretend m is positive, and so the slope is positive here. This intercept is b. Let's say this is my specific number t. This number here would be then mt plus b. What's the distance traveled? Well, so I can't use this formula anymore because it only applies when it's a constant rate. However, I can use it if I kind of cheat. Well, it's not really cheating. If instead of the rate here, a constant rate, I use the average rate. What's the average rate here? It would be halfway between these two numbers. It would be the average of these two numbers, the extremes, if your speed is a linear function of t. What is the number halfway between them? Well, I got to take their average. I got to add them and divide by 2. mt plus b divided by 2. 1/2 mt plus 2b over 2 would be the same as b. That's what that number is right there. If you had specific numbers for m and b, you could find specifically what that is, although it would still depend on t. If I take that average speed and multiply times the time elapsed, that should give me the distance traveled. Dist of t should be that average speed, 1/2 mt plus b times the time elapsed, t. It's an average rate times time elapsed. Multiply this out, and you'll get 1/2 mt squared plus bt. I claim that's the same as the area under this graph. Do you believe me? Split the area into two regions, this rectangle and this triangle. The area of the rectangle is base times height, b times t. The area of the triangle is 1/2 base times height. 1/2, its base is t. What's its height? What's this right there? Its height would be this number minus that number. mt plus b minus b is mt. 1/2 base times height, mt. Okay, that's the same as 1/2 mt squared. And look at this. The sum of that and that is the exact same thing that we got by doing the average rate times the time elapsed. That should seem kind of wild. And it's true, the area under the graph gives you the distance traveled. Something else to note in both cases here. This is really important as well. If you differentiate this distance function with respect to t, we're back to the first case here at a constant speed. Dist prime of t, c is a constant, you get c, you get the speed. In case one, the speed was constant. Same kind of thing happens here. If you differentiate this with respect to t, find the derivative, bring the 2 down in front. 2 times 1/2 is 1. Subtract 1 from the exponent. Derivative of bt is b. Hey, that's the same as the speed function. mt plus b, that's the speed. That's no accident. It's no accident. The area gives you the distance traveled, and also the derivative of the distance traveled is the speed. These are absolutely fundamental connections that generalize to every other situation related to this. This is really key, but it's easy to get confused. And it's easy to kind of get it, and then all of a sudden realize, wait a minute, now I forgot. You know, you kind of feel like, oh, I do get it. And then like 30 seconds later, it's gone. So you have to continually think about these. Let's end class by doing another example. Let's say the speed is t squared. And we're trying to estimate goal. Let's estimate the distance traveled from time 0 to time 4, say. What I've just been saying, the answer, whatever it is, should be the area under the graph of this function. From 0 to 4. This graph is a parabola. When you're out to 4, the speed's going to be up to 16. The answer is going to be the area under the graph. Okay, that will be the answer, whatever that area happens to be. I mean, we can try to ballpark it. It's certainly less than 4 times 16. It's certainly less than 64 by more than half. It's certainly less than 32, you could probably say. What if we don't have any other way to estimate the area besides just trying to roughly approximate this with, say, rectangles? That's an approach we can take. And in fact, you'll see this approach in the book. We could split this interval from 0 to 4 up into, say, 4 pieces. 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And within each of those subintervals, we can go to the right-hand endpoint, go up to the graph, and use that point to make the top of a rectangle, like this. For each interval, go to the right endpoint and make a rectangle with that height and a base of 1. Obviously, if you add up the areas of these rectangles, the answer is going to be too big. It will over approximate the green shaded area, but it's a start. And it's maybe a start that can generalize. Maybe I can generalize it by making the rectangles skinnier, for example. Make them more rectangles that are all skinnier, and that might approximate the area under the curve better. The width of each of these intervals is 1, but let me just give it a symbol at first. Let me call it delta t. Each of these widths is delta t, change in time. The area under the curve will equal dist of 4. And this area under the curve is going to be approximated as the base of each rectangle times the corresponding height. The height of the first rectangle is speed of 1, because the right endpoint of the first interval is 1. This height right here is speed of 1. It's 1 squared, or 1, in fact. The height of the second rectangle is speed of 2. The right endpoint of the second interval is 2, and its width is still 1. The right endpoint of the third rectangle is speed of 3. That's the height. Go to the right endpoint, go up to the graph. That is the height of that rectangle. Its base is still 1. And for the fourth one, its right endpoint is 4. Go to that right endpoint, go up to the graph. That is the height of that rectangle. Speed of 1 is 1 squared. Speed of 2 is 2 squared. Speed of 3 is 3 squared. Speed of 4 is 4 squared, because the speed is t squared. Multiply each of those times 1, you get 1 plus 4 plus 9 plus 16. 30 meters, say, would be your estimate, your initial estimate for dist of 4. Okay, based on this, it's called a right-hand sum, because I was using the right endpoint of each interval to estimate the area under the curve. You can see again from the picture that because these rectangles are all above the curve, it's going to give us an area too big, and therefore a distance that's too big. This answer of 30 is too big. How do you find the exact right answer? That's something called the fundamental theorem of calculus, and that's what I'll end class on. The fundamental theorem of calculus says that the distance traveled is actually take this function and find an antiderivative of it. General antiderivative here is 1/3 t cubed plus c. Plug in 4 into that function and then subtract what you get when you plug in 0. Why 4 and 0? Because those are the starting values of t and the ending values of t. This is actually going to be 1/3 times 4 cubed. I can take the c to be 0 here when I do this calculation. 1/3 times 4 cubed minus 1/3 times 0 cubed. This simplifies to 64 thirds, which is what, 21 and 1/3, 21.3 repeating meters. That's actually the exact answer. Now, I don't have enough time to explain this fully. I'll explain it much more fully on Monday, okay? But for the moment, in the homework that you'll have due Monday from section 5.1, it's more related to what I did here. And there's plenty of examples in the book where they show you different rectangles approximating different areas under curves. Make sure you get that basic idea down and be able to approximate those areas with summations like this. Okay, it's a lot of information again, but again, we reviewed some stuff, though it was trickier, and now some new stuff. Do the reading, that'll help. All right. All right, that's it.